we only
Mhm.
know string theory in perturbation theory. So you're in
Mhm.
this kind of, situation where yes, the subject is old, maybe over 50 years old, but you still don't know the basic objects of the theory, like when the string coupling constant is 1.1, or the volume of your internal space is of order the string length. You just have no way of calculating things. And what do you do in that situation? Like, you just have to continue developing the theory slowly.
Our guest today is Dr. Raghu Mahajan. He did his PhD from Stanford University and currently he is a theoretical physicist at ICTS Bangalore. He has worked on the island's approach to black holes and is currently working on instanton physics. He also spent some time at IIT Delhi in India after securing All India Rank 1 in the entrance exam for IIT. We will also have a brief conversation about his experience at IIT Delhi. So let's welcome Dr. Mahajan on the podcast and see what he has to say. So, first of all, Dr. Mahajan, welcome to the podcast. It's nice to have you.
Thanks for having me, Hassan.
So, I want to start with your time at IIT. When you were in IIT, I have heard different stories from different people that you were considered a very very smart person at IIT. So, can you describe a bit? How was your time at IIT? And I also want to ask you that. Did you know that you want to do theoretical physics before your time at IIT, or did you develop that particular interest when you were in IIT?
Yeah, I'm happy to talk about that. So, in IIT, I was in IIT Delhi for 2 years and I was enrolled in the computer science major there. The reason for that was, even though I sort of knew that I wanted to do physics, at the time the JEE results came out, but somehow at that time I was not able to go against the societal pressure. In India, people want you to do engineering, and even though I knew I really liked physics, I somehow didn't have the strong will and determination at the time to go against societal expectations. So initially I had a plan that I'll do a bachelor's in engineering and then do a PhD in theoretical physics. But I did not like the physics department at IIT Delhi at all. um, Basically there were like clear problems with that at that time. um, so therefore, I decided to apply for a transfer admission, which I knew could happen to some of the US universities, and I was lucky to sort of go to MIT at the end of my second year at
Mhm.
IIT.
I see. So, can you tell me what sparked your interest in physics? Did you read a book or did you follow someone that sparked your interest?
It wasn't really books, actually, it was two teachers that I had. So there's this, so in 11th and 12th class, in at least my generation in India, almost every kid in the north at least didn't go to school, but we went to these so-called coaching classes to just prepare for the IIT exam. And I used to go for physics and chemistry coaching. And the physics teacher I had there, Mr. Arvind Chauhan in Chandigarh, he was really, really good. He he basically taught in such a way that you just understood everything. Uh, and he also encouraged my interest in physics by giving me some advanced books to read, like advanced mechanics, advanced electrodynamics, that went beyond just the syllabus of the IIT exam. So that kindled my interest. And then I went for the physics Olympiad at the end of class 12. There is this International Physics Olympiad, and the Indian team is trained at this Homi Bhabha Center in Mumbai. And at that time, Professor Vijay Singh was running the Olympiad program in physics. So he was a very influential figure, and I even did some research with him while I was at IIT Delhi. But as a prelude to that, my interest just in the mathematical sciences had been kindled by my father. So he had
Mhm.
said one thing, which I still remember, like in class 4 or 5. He had basically said that if you understand math, you'll understand all the other subjects in school. So somehow I sort of took that to heart, and I was basically doing maths a lot. No physics till class 11th, but then when sort of I joined the JEE coaching, I sort of realized that theoretical
Mhm.
physics is the kind of math I like, and that kind of became the natural um, direction to follow.
I see. So, I do understand your interest in theoretical physics, but did something happen that made you interested in particular, in string theory? So, how did you get interested in string theory?
Uh, I guess it was kind of by almost by default, because I liked math, and so I kept doing math. And I went to MIT as an undergrad, and there. I did some undergrad research with the faculty there at the time, Alan Adams, Hong Liu, John McGreevy. And that was interesting. And then I joined, Stanford for my PhD, also wanting to continuing do research. It wasn't specifically string theory in the beginning. It was general, just high energy theoretical physics, which has a broader ambit than string theory. So, initially I did a lot of projects just in quantum field theory, inspired by condensed matter problems that my advisor, Sean Hartnell, was working on at the time. So, yeah, and then I realized that fundamental problems of quantum gravity have not yet been solved, and string theory is the most promising candidate we have right now, and it's mathematically consistent. So, why not work in it?
I see. So, did you ever have second thoughts that, okay, probably one of the contenders of string theory may be the right theory?
Well, I have to say, I have never seriously engaged with any alternative theories like loop quantum gravity or anything.
Hmm.
So I'm not an expert in those topics and what all has been achieved. But just in terms of, the results that you hear. So string theory, for example, if you forget about all the details, there are two, I think, remarkable cornerstone achievements of string theory. One is just the formula that started it, the Veneziano amplitude, or the is generalization, the Virasoro-Shapiro amplitude, which is a formula for 2 to 2 scattering of massless spin 2 particles. It is reduces to Einstein's gravity in a limit, but extends it. It is has the Einstein formula is just a limit of it, and every possible consistency condition that you can think of is satisfied by this formula.
Right.
Okay, and that's really a remarkable fact. I mean, this is not much stated in public debates on string theory, but I don't think there is any other formula out there that can sort of has that kind of depth. So it has the
Hmm.
correct energy behavior, it has all the correct poles, it has the correct unitarity properties. You put all these things together, it's pretty constraining. Okay, so it's a very non-trivial fact that the first formula that started string theory has such depth. Okay, so that speaks for the mathematical depth of the subject. And the second, of course, is the microstate counting of black holes. Okay, extremal black holes, but area over 4G Newton, it's established beyond doubt in many cases that string theory gives you the correct counting of black hole entropy. And I don't think my knowledge is limited, but I don't think any of the other contenders, the successes of those theories come close to these two sort of remarkable
Hmm.
formulas. And then, of course, the study of extremal black holes and their entropy led to holography and ADS-CFT and all that, which in turn has had a lot of influence just on, lowbrow quantum gravity, which is what this islands approach or the wormhole was an offshoot of.
I see. Yeah, we will talk in more depth about, the arguments in favor of and against string theory. But right now, I also want to, ask you this question that you have worked on the islands program, of black holes. So I also want to ask you that how did you become interested in that particular approach? Did something convince you that there may be something there that is, worth working on?
Well, I think calling it the islands approach, first of all, is maybe not the right
Hmm.
term to use because the
Hmm.
islands are
Yeah.
not really fundamental in the problem.
Hmm. Right.
Uh, yeah, so I wouldn't really phrase it that way. The thing that we have learned through these last 5 6 years of development is the fact that if you ask the right questions in holography, just on the boundary theory, it could be about a 2 point function in a thermal state of some simple operator, or it could be the von Neumann entropy of some subregion in the boundary theory. So you set up the problem on the boundary and you just let the path integral do its job. Like, the path integral, you evaluate it in the saddle point approximation, and you pick up the relevant saddle points, which can be different at early times, at late times. And that is what gives you all these results. So the new fact is that there are extra saddle points, which are, by saddle point, I just mean some geometry with matter fields that is solving the Einstein's equations. Okay, so that people just had not realized that these interesting solutions are interesting, like, so that is the new thing. So in some sense, it's very vanilla. It's not a very path-breaking, paradigm-changing event that happened. We just realized that there are these other solutions that people just had not found before.
Mhm. I see. And I also want to ask you about this result, which was, declared in this paper by Randall and Andreas Karch and some other people, that, on the face of it says that, this island, okay, this is the name that I'm using right now, but the islands
Yeah.
approach, it may be inconsistent with long-range gravity. So what do you make of that result? I mean, is that result a serious blow to this
Uh,
particular approach?
Well, I think again there are subtleties, and well, Subrat is my colleague here. I have had long debates with him. Subrat Raju is one of those authors. The point is that yes, the calculations that have been done are in models with, where a gravity region is coupled to a path, and that's a slightly non-standard setup of gravity. I don't think they claim that islands are inconsistent in that setup, or islands are in general. That is not the claim. The claim is that um, the proper subalgebra of which you are computing the entropy has not been properly identified. That is what they say. So, what they're saying is if you didn't have a bath and you have a black hole which is evaporating in a spherically symmetric fashion, if you compute the entropy of the whole boundary, of course, you're going to find a flat curve. There is no debate about that because the whole boundary is keeping track of all the degrees of freedom.
Right.
So, I mean, they agree that if you didn't have a bath and you have not, in a smart way, separated the system into two parts, then I don't think anyone will disagree that the entropy of the full boundary is just zero at all times. The question is, can you identify two subsystems smartly who will follow, the page curve? And all this bath does is kind of separate the radiation degrees of freedom from the black hole. Now, that said, yes, it does introduce this qualitative feature, but I really think it's just a red herring. Um,
Okay. So what you're saying is that there needs to be some more clever separation between the degrees of freedom.
Basically, what I'm saying is if you didn't have a bath and you want to, and let's say you just have a small black hole in ADS that evaporates. Okay.
Right.
Now, on the boundary, the state is pure at all times. It's just pure state black hole from collapse and is just evaporating in a spherically symmetric fashion.
Right.
Even once you have that, there is no geometric subregion that is isolating the Hawking radiation. So
Hmm.
therefore, you cannot use the Root-Hakenagi formula to study the entanglement entropy of Hawking radiation. But I don't think these authors are claiming that it is not possible to separate those degrees of freedom. It's
I
just that
see.
that separation has not been done yet cleanly in a system without a bath.
I see. If I so correct me if I'm wrong. If I remember correctly, what they were saying is that the gravitational effect of the degrees of freedom which are in the islands will be felt by the region which is outside the island. But the thing is that the degrees of freedom in these particular regions are supposed to commute, and that's inconsistent with the
No, no,
earlier
that is not what
statement.
they are saying. No, no, that's not what they're
Okay.
saying. I think that is maybe the complaints of Samir Mathur and some other people. Uh,
Okay.
that again is basically, see, the message, if there is one message that I want to convey about this whole wormhole story, is that one should not try to make conclusions based on the semi-classical geometry. The island that it exists is a output of a saddle point calculation. Now, one shouldn't try to ask of it more than what it's doing for you. It
Okay.
was a calculational device that gave you the page curve, and it gives you some other things like this Pennington, uh, Schenker, Stanford, Yang paper also showed these effects of the PETS map that you can, affect the degrees of freedom in the island by acting with a complicated operator on the radiation. And again, that happens via a wormhole. So the question is the point is that you should first set up a quantity that you want to compute, like a number, like a 0 or 1. Is this degree of freedom going to be affected by this particular experiment that I'm going to perform? And then you set up the whole thing on the boundary and you let the gravitational path integral do its job. And there may be interesting kind of wormholes that pop up in the situation, and those effects then you may or may not be comfortable with. in your Lorentzian semi-classical picture, because we are so tied to thinking of a causal structure of a fixed space-time that these effects kind of, boggle us. But there is nothing really inconsistent about them because it's quantum gravity. So, the geometry of the space-time itself is undergoing large fluctuations in these subtle observables. So any reasoning that you use based on something like, oh, it's space-like separated or something, is necessarily just in one geometry, which is not true, in these late time regimes. Like you can say that the wave function of gravity has kind of support on very different geometries. So therefore, to mm, draw conclusions from it, you just need to follow the rules of quantum mechanics and not some semi-classical intuition that you might have had.
I see. Okay, that makes sense actually. Okay, so you mentioned Samir Madhur. So I also want to ask you that if you have any, opinion about the program that he has been leading for the last 20, more than 20 years, which is the Fuzzball program.
Uh, Again, I'm not an expert, but
Hmm.
I think there are, challenges for the fuzzball program. Like I mean, they have, I think, fully identified the microstate geometries in the so-called two-charge fuzzballs. But those fuzzballs have classically the black holes have zero area. So they kind of have a small amount of entropy. And even, they don't claim that for the three charged black holes, which are the big black holes with a macroscopic horizon, they don't have a full entropy count using these microstate geometries. Okay, now that is not to say they won't find it one day, but there's also interesting challenges to that program from the uh, just quantum chaos perspective and eigenstate thermalization and so on. Because these fuzzball geometries are kind of special. So they don't exhibit the kind of strong chaos that we expect black holes to, exhibit. So I think it remains a challenge for them to, complete the program and, also show how the classical black hole would arise because, LIGO sees black holes merging with each other. So a black hole horizon does exist. Undoubtedly it does exist and is described by Einstein's equations. So if you have a proposal where you're saying that the horizon is just not there at all for any black hole, it is a challenge for you to reproduce the results of LIGO. And now it's kind of cheating to say that, oh, all these effects are just inside the horizon or just, you don't see because the horizon of two black holes when they're colliding and orbiting each other is a dynamical, thing. It's not like one horizon of a static black hole. So I think there are these challenges and it would be nice if they can address these challenges in the future. It
I
remains a
see.
possibility that these two pictures are consistent.
Hmm. Well, I do know some of the criticisms on the fuzzball paradigm that are, for example, done by Suvrat. I didn't know about this particular criticism that you're saying that LIGO shows that. I mean, okay, we do see the horizon in some sense, but they will interpret it in a different way. They will say that, as
Yeah,
you were
but they
saying,
have this
that these.
vague word called fuzzball complementarity.
Yeah,
And
exactly.
that's basically supposed to mean that when you expect to see black hole properties, you do see them. But you have to
Yeah.
prove it. You can't just claim that there is something called fuzzball complementarity.
Well, according to what I understood, so I did talk to Samir Madhur, and he was actually acknowledging this thing that yeah, we do have to prove it. So yeah, probably they will. Okay, so the major part of this podcast is going to be about the field of string theory as a whole. So I do want to divert the discussion to that
Yeah.
particular part. So okay, so this may be a vague question, but then we can move to some more
Mhm.
specific discussions. How do you see the state of string theory, in this particular decade in 2020s? Do you think that the field as a whole is moving forward? And if that's the case, then what are the most promising areas and most important problems to work on in this particular age?
I think it is definitely moving forward, slowly but surely. That's one thing to say. And the other thing to say, is that we have had string theory for 50 years, uh, and we still don't have a fundamental formulation of the theory. It's like if you knew GR only at the level of perturbative gravitons and perturbative gravity waves. You didn't know what the Einstein-Hilbert action was. you didn't know that there are some space-time geometry and Lorentzian geometry underlying the whole structure. We only know string theory in perturbation theory.
Mhm.
We do not know what the mathematical structure underlying string theory is. We still don't know it. So, all these critics on social media and media in general who rush to say that, we should not do research in string theory, they have to realize that we don't even know what the theory is about. It is in such a primitive stage of development, and yet it has given these remarkable formulas, like I was mentioning, like the Virasoro-Shapiro amplitude and
Mhm.
the area over 4G Newton for extremal black holes. These are not insignificant successes, and you've been able to do this without knowing what the theory is really a theory of. So, imagine what all things you could do if you really knew the fundamental formulation of string theory. So I think this point is underemphasized. I mean, there has been a lot of work in string theory, but despite all that, we only do perturbation theory. You only do expansions in small alpha prime or small G string. And or you can do expansion in 1 over G string. Okay, the string coupling is infinitely big. Then maybe you have some results like S duality and so on. But if the string coupling is 2.3, you have no idea how to compute observables.
Right. You mentioned the social media thing. I mean, that's a whole rabbit hole that we can go in. But I think a lot of, the criticism of string theory on social media is very, very ill-informed. And I think probably the biggest reason is that a lot of critics who are actually leading this criticism themselves are ill-informed, and they haven't, interacted with the theory in, I don't know how to say this. In reasonable depth before talking about these things. But what I want to ask you, as I also asked you before, that right now in this day and age, what do you think are the most important areas to work on? For example, I think getting de Sitter spacetime may be one of the big areas. For example, modular stabilization may be one of the areas. So, what areas do you think are
Yeah.
most promising areas to work on right now?
Again, I would say, yes, those are important questions to think about, like
Hmm.
constructing a de Sitter vacuum, constructing solutions that have these large separation of scales and so on and so forth. But uh, again, those will be limited to perturbative techniques in nature. So one of my sort of thinking about the subject is that we have to really understand the theory, right? That's a different goal than trying to find the standard model or trying to find de Sitter space in string theory. So I would say that yeah, these are the two. So these are two of the directions. There are many other directions. So first one is like understand string field theory better, right? We string field theory still is formulated only as a perturbation theory. We don't know what is it ultimately a theory of, and string field theory is just a systematization of our knowledge of perturbation theory in string theory. Okay, so that is why I've worked on these instant-on effects, and I continue to work on them because they teach me more and more about, the subject of string field theory. I mean, the second thing, of course, is, you know, again, this is underappreciated how little we know about string theory. Most of the backgrounds in ADS-CFT involve Ramon-Ramon fluxes, involve Ramon-Ramon fields turned on in the background. And the standard formalism, this Ramon-Neveu-Schwarz formalism of string theory, cannot support a Ramon-Ramon background. Like that formalism just breaks down when you have Ramon-Ramon fields in the background. So you need to develop new techniques to deal with these, Ramon-Ramon backgrounds. And that actually connects to some string field theory work that people have been doing recently. Like people have been trying to sort of construct perturbative Ramon-Ramon vacua in string field theory. And then and you mentioned scale separated vacuum and de Sitter space. All those solutions also have Ramon-Ramon fields in the background. So if you want reliable constructions of de Sitter space and so on, you need to better understand, fundamentals of corrections, to string theory, uh, the standard stuff we say, but you have to, use new tools to work on that.
Right. I want to ask you something about string field theory, but before that, this comment about Ramon fields, as you rightly said that the RNS formalism breaks down, but we do have pure spinor formalism that does deal with Ramon
Yeah,
fields.
that does deal with it, but as far as I understand, like the method of computing amplitudes there is not
Hmm.
known. So it gets the spectrum right. You can input the things, but then you
Right.
don't have all the computational machinery that comes with the RNS formalism. So I think people are still trying to figure out how to compute scattering amplitudes in the pure spinor formalism. So yes,
I
there is a
see.
formalism and that needs to be developed, but there is work to be done, in that direction there
I
to
see.
really put meat on the bones of, the pure spinor formalism.
Right. So you also mentioned the fact that we need to understand string field theory better. So do you think that, okay, this is something that I have felt. Please let me know if you agree with this. So I see that the number of people who are willing to, okay, working on is a thing that comes after it. But I've seen that the number of people who have time to learn string field theory is very small. Do you think that this is a correct observation? Okay, so one of the reasons that people give me is that uh, there are not a lot of problems such that you cannot solve that problem without string field theory. So do you think that this is correct or not?
Well, it's hard to say, what approach works and what doesn't work. I think
Mhm.
it's clear that it's a rich subject and it's an important subject and it needs to be developed. Now, there's a very small community of people who work on the subject, and there are not that many people in the US now. Okay, Boston has a couple of people, Barton Zweibach and Sheehan has been working on it recently.
Right.
But largely, the field is not active in North America. In Europe, there are more people, doing these things. And in India, of course, there's a couple people doing it. Uh, so, it's hard to say that people are not spending time because if the field is small, then only the students of those respective faculty who are doing research in that will kind of follow, do problems in that field. Um, Now it clearly is important because it is being used to, turn on RR background fluxes and do various things. So like all these instanton calculations, required string field theory input to fix,
Mhm.
to fix some quantities in holography that had not been fixed for the last 30 years.
I see. I mean, as I was saying before, that a lot of people tell me that they don't see a lot of incentive to, learn string field theory. But as you were saying, that if it turns out, which is turning out to some extent, that if we are able to connect string field theory to other problems, for example, you are talking about instantons. I recently saw a paper by Xi Jin where they were talking about using string field theory methods to construct, for example, boundaries in boundary CFTs. So, I mean, if you can do these kind of things, then do you agree that more people will come to this subject because they will see the incentive to learn it?
Um, yeah, I mean, it's hard for me to predict what people will do and what people will do. All
I
I can
mean,
express is
sure,
the hope that people, more people maybe should think about it because it's an important and interesting subject. And only if a critical mass of people work on it, that you circulate ideas and um,
sure.
you generate new ideas. Um, it's basically string field theory is just a fancy name for, organizing perturbation theory and string theory better and dealing with
Right.
so-called infrared divergences.
Hmm.
It's nothing more than that. And so in some sense, everyone who is working on string perturbation theory is working on string field theory. Like whenever they encounter some IR divergence in the problem that, that you want to solve, you probably will have to turn to string field theory to, resolve those things.
I see.
It's just a version of, using quantum field theory logic to address certain infrared divergences in string theory.
I see. Okay, so and now I want to ask you about a particular problem in string theory, and I do okay. So I'm much junior than you, but I do understand some of the nuances of this problem. But I'm still going to play a devil's advocate to ask you this question, and let's see how you respond to this question. So a lot of people on social media, and this is coming from some of the better criticisms of string theory, not the naive ones. So we did talk about this thing just a couple of minutes ago, that there is this problem of constructing the sitter vacua in string theory. So if someone says that you have not been able to construct the sitter vacua in string theory, that's a big blow to string theory. How would you respond to that particular statement?
I don't know. Again, these things are very sort of short-sighted. I mean, it's not a no-go theorem that, one day you will not be able to find a de Sitter vacuum. So people are trying, and you realize that as theoretical physicists, we have to be more patient, like, maybe like mathematicians or our experimental colleagues. They work on problems for, 20 years, 30 years, and they're patiently, keep chipping away at it. Whereas, because theoretical physics had such good luck in the 20th century, we kind of have become used to like a big thing happening every 5 years, every 10 years. When a field matures, that time scale kind of expands for big discoveries. So it is very important to realize that the time scales for these big goals may be bigger than what they were in the 40s or the 70s or the 90s. And that happens to a field as it matures. Like Fermat's last theorem, like, they took 300 years to prove it. Like, would you have said that, mathematicians should stop working on it in the 1800s? So there's sort of a psychological, almost cultural issue at play here, which, yes, there is no maybe 100% foolproof de Sitter vacuum yet, but there is no 100% proof that it doesn't exist. So, what would a sensible person do? A sensible person would sit down with his pen and paper and his computer and try to work it out, instead of trying to have just noisy debates on social media. I mean, like, what's the point?
Right. I mean, won't you also say that when it comes to, for example, the string moduli space, and I'm just talking about the part where you have, that's the volume of the compact dimensions, and you also have the, the string coupling constant. Don't you think that we have explored such a tiny part of that moduli space yet? Because that's the part where we can actually do some calculations. And okay, where there we know that, okay, they may be not de Sitter vacuum, but there's this whole big moduli space that we have not explored yet.
Well, exactly. That comes back to my original point, which is that we only know
Mhm.
string theory in perturbation theory. So you're in
Mhm.
this kind of, situation where, yes, the subject is old, maybe over 50 years old, but you still don't know the basic objects of the theory, like when the string coupling constant is 1.1, or the volume of your internal space is of order the string length. You just have no way of calculating things. And what do you do in that situation? Like, you just have to continue developing the theory slowly, and you have to be patient, and that's it. Like, it's like this question was asked to Ashok Sen in one of the online strings meeting, I think the South Africa one, where, I mean, there was the similar kind of question in a public session, and he basically very nicely just said that as long as the theory is consistent, there is no reason to not work on it. I mean, there
I
is
do
no
remember.
mathematical
Yeah.
inconsistency, and the math is beautiful. It touches upon various fields of mathematics, various other topics in physics, like in topological field theory, in all these sort of modern constructions of QFT. Like, all these ideas kind of, circulate in the same room. So, you have to realize that there is a certain depth and a certain uh, maturity to the subject that maybe, people who don't work on it don't appreciate how beautiful these connections are.
Right. Um, so I did ask this question to another guest, Joseph Conlon, and he said the same. One thing that I was kind of expecting that he said that if I knew the answer to this question, I would be working on it. But I'm still going to ask you this question, and you can just tell me your guess. So until now, we have had two superstring revolutions, and they came in because of some big breakthroughs. Uh, do you think that Oh, sorry. What do you think is the possible problem such that the solution to that problem will give you the third superstring revolution?
Well, I think this is again one of these things that, you never know you are in a revolution
Hmm.
until it happens.
Right. But if you
Basically,
had to take a guess.
yeah, maybe I wouldn't want to. Yeah,
Okay,
maybe.
sure. It's
Because
understandable.
you see, even the second superstring revolution kind of happened with a bunch of different ideas, coming together at the same time. Like Ashok's paper on S-duality in heterotic string on T6, Pochinski identifying Ramon charges in D-branes, Seiberg-Witten working on the n=2 supersymmetric theory. Like, these are kind of spontaneous events. Like, You cannot predict these things. I mean, yeah. And one has to remember, for
Right.
example, before the first superstring revolution between 67 and 84, how many people were working on it? I think basically John Schwartz was the person driving the field for like good part of a decade, like when no one else was working on it. So he was just sort of, just going at it, going at it, going at it. And he came up with these models, in the 70s. So, one has to have that perspective of silent work and not all the time expecting a hype and media attention.
I see. Okay, so one more thing that I want to address here is that a lot of people who are working on quantum gravity have this expectation, and I don't think that this is a very misguided expectation. They think that whatever the correct theory of quantum gravity is, that theory should not have space-time as a fundamental entity. Space-time should be emergent from something more deep. So, do you think that this will be true in the future? Or in other words, I also want to ask you that do you think that string theory does give a sign of such an expectation to be fulfilled?
Probably, I would say I would bet on it that yes, space-time will not be fundamental. Basically because the graviton is the lowest mass state of a string. I mean, the string has all these massive string states. And if you're in some crazy non-perturbative situation, there is no, I mean, all those fields will be equally important as the space-time metric. And this is related to my very initial comment and a comment that I've made a couple of times, which is we don't actually know the fundamental degrees of freedom of string theory. We just don't know. We know it's not just a theory of strings because there are branes and membranes and what else there is. Uh, yeah, so we don't know, in what variables the path integral of the full string theory will be written in. Like, to just give you an example to drive the point home, before Einstein or before Hilbert or these two people, you didn't know that the path integral for gravity was going to be written in terms of something called a metric of a space-time manifold. Gravity was a force,
Right.
so it needs sort of a paradigm changing shift of idea to introduce that variable. And in string theory you don't have that. We don't yet have what the metric is, what the metric was for general relativity. That corresponding variable for string theory we don't have.
I see. But don't you think that in order to make sense of what a path integral is, you need space and time?
Not really, no. Why? We can just
I mean,
have
so for
path
example,
integrals over like matrices, right? Like for example, a classic example are these toy models where you just have like a path integral over 11 matrices or 10 matrices in this
oh,
IKKT
okay, I
matrix
see.
model, and the whole thing just emerges from that, right?
Oh, so you were talking about those kind of things. I thought that you were talking about path integrals that involves fields, because if you have fields, then you should have some space time. Isn't that the case?
Yeah, yeah, sure. But the path integral doesn't need to be over space-time. The path
Hmm.
integral could just be over some matrix degrees of freedom, for example, which don't
I
even
see.
have a time in them.
I see. I also want to, have your opinion about. So okay, so until now, a lot of calculations that people have done in order to construct these string vacua do take advantage of the fact that we do know how to do a lot of calculations when supersymmetry is there. But do you think that we need to explore more in the the areas where supersymmetry is not there? Although we don't have that much calculational control there, but do you think that those areas are worth exploring more?
Well, for example, the de Sitter question necessarily involves breaking supersymmetry at the last step, right?
Hmm.
So we
Right.
definitely will have to, tackle those things appropriately. Now, again, I'm not an
Right.
expert on constructing de Sitter solutions, but I think the answer is obvious that yes, we do need to go beyond just supersymmetric compactifications and find ways to, compute things in those cases.
I see. I mean, this also brings me to another misconception about string theory. A lot of people assume that string theory necessarily needs supersymmetry, which is not the case, of course. Because another thing that happens is that when you say that string theory can happen without supersymmetry, a lot of people who have very naive understanding of string theory will say that, oh, you're talking about bosonic string theory, but it has tachyons. But no, I mean, there are these heterotic string theories without tachyons and without supersymmetry, right? So do you have any opinion on how to tackle this misconception in the popular audience?
But I think to that, we should just say that, if a theory has a symmetry,
Mhm.
doesn't mean that all the states of that theory are also invariant under that symmetry, which is basically what it means for supersymmetry to be broken in a compactification.
Mhm.
You're looking, the hydrogen atom has an SO3 rotation symmetry, but not all its wave functions are SO3 symmetric, right? I mean, you have a P
Right.
wave which transforms in a certain representation of SO3 or D, S, whatever, F.
Mhm.
So it's the same way with supersymmetry. Even if your Hamiltonian or your Lagrangian has supersymmetry, does not mean that every classical solution of the theory has to have supersymmetry,
I see.
right? So that
I
is
see.
what would it means that if you consider a compactification just as completely crazy and does not even preserve n equals 1 supersymmetry in 4D, there are probably many such things.
Mhm. I see. So I also want to do yes, some, well, at least some discussion about at least the idea of the swampland program, right? I don't
Mhm.
need to, we don't need to go into a lot of details, but for the audience, can you tell the basic idea of what the swampland program is? And then I also want to talk to you about, some of the conjectures which are kind of controversial, but we can talk about it. So, but for the audience, can you explain what the swampland program is? I mean, just the basic idea
Well,
of what it is.
um, again, I have never worked on the swampland program. I've only heard very few talks about it. But from what I understand, people study, lots of compactifications. At least that was the original idea, that you study lots and lots of string compactifications and you find some patterns that, for example, there is the weak gravity conjecture, or there is the conjecture that no global symmetries in quantum gravity. These kinds of things came from studying the swampland program, and there are some that are probably true, like these two that I mentioned.
Mhm.
um, so that's what I understand. Like, people try to sort of make claims based on various examples that one has, and tries to say that these are the features that a low energy theory should have in order to be UV consistent within the presence of gravity.
I see. So, as you were saying before, that there is no proof that there will be no de Sitter in string theory. However, there is this conjecture in swampland, the swampland program, which is again, it's very divisive. People, all of the people don't agree with it, and the conjecture effectively says that there is no de Sitter in string theory. So, what is your gut feeling about that conjecture? Do you think that this conjecture will
I
be true?
I don't know. It's a conjecture that people have made. Maybe people should try to prove it rather than just state it as a conjecture. Um, uh, as far as I know, like, just from the grapevine, like, neither the conjecture nor the full constructions are 100% solid. So maybe both camps should try to work on their respective things and try to solidify their arguments, and instead of arguing over incomplete facts, try to do the homework and then come to the debating stage.
I see.
I really
Okay,
think
so
that a lot of work needs to be done to really make these things um, uh, like more um, yeah, to me these debates are a bit meaningless if you're not backing up your arguments with very solid uh, proofs. Like, yeah.
I see. Okay, so you mentioned before that you are working on instantons and you are doing that work to, understand the structure of the theory better. So, can you, well, briefly explain what kind of work you are doing? I do understand that you are working in this Sine-Gordon theory and some other instantons, but can you briefly explain that, what is your research program right now when it comes to instantons?
Yeah, so as we know, string theory has instanton effects. These are d-instantons. These are like d-branes, but where all the space-time directions have Dirichlet boundary conditions. So these objects contribute effects of order e to the minus 1 over the string coupling to any string observable. Like, could be a scattering amplitude, could be a partition function, anything. And the question is to just calculate these effects. So these are very, very small effects. These are smaller than any power of the string coupling. And one of the points is to do these calculations so that you can perform stronger checks of holography. Uh, so there's a ADS and there's a CFT, or a more general, there's a string theory and there's a gauge theory, dual of it. The question is, can you compute instant-on effects separately in the two theories and compare the answers? Okay, so that's like, basically coming from the side of doing very, very strong checks of gauge string dualities or things like S duality. Now, basically, that's what people have been doing. Like it was started by this paper of Balthazar Rodriguez and Yin, and then Ashok Sen wrote a lot of papers. So my work has been to, extend that to some more simpler models of holography that were discovered in the early 90s or late 80s, these so-called minimal strings, and apply them to situations with supersymmetry to understand whether supersymmetric situations could be different. So yeah, we are basically trying to do more cases if those cases have, new qualitatively new features. Like I think there is still a lot to be done. So for example, we had a paper on this so-called type 0b superstring and instant-on effects on that. And currently we are generalizing it to type 0a. And it's not as mundane as it sounds because there seem to be some qualitatively new features, in understanding the instantons in this situation. For example, it's sort of preliminary, but sort of to say that there are different kinds of gauge groups and different kinds of, you know, subtleties in the string field theory gauge fixing procedure than that one has to do. And I'm
I
also
see.
slowly starting to think about these Ramon backgrounds in the context of string field theory and calculating corrections, in those backgrounds.
So it seems a bit, surprising to me, but you can explain why it shouldn't be surprising.
Yeah.
So correct me if I'm wrong. So type 0A and type 0B, they come with
Yeah.
tachyons. So what is the motivation to understand instantons in those theories?
Well, so these are type 0A, type 0B theories in 2 dimensions or lesser. I should have clarified, not in 10 dimensions, but
Oh, okay. I see.
there are these 2 dimensional, low dimensional critical string theories, which do
Mhm.
not, in fact, have a closed string tachyon. Now, the d-instantons in them do have open string tachyons, but that's okay. Those are just the regular instabilities of the d-branes. And
I
the
see.
dual
I
theory,
see.
the gauge theories have also basically there is something called an effective potential, and the effective potential has maxima rather than minima. So an eigenvalue sitting at a maximum of its effective potential is like an unstable d-brane.
Hmm.
So it's important to note that in this minimal string theory or minimal superstring theory or this C hat equals one setting, there are no closed string tachyons.
I see. So, as you said before, that you are also, trying to understand the Ramon fields. So, are you trying to understand the Ramon fields in this 2D setting or in the 10D setting?
No, that would be in the 10D setting. Yeah. I think even in
Okay,
the
I
2D
see.
setting, one could do something, but I'm not sure because there are Ramon fields in the 0A and the 0B,
Hmm.
these low dimensional, backgrounds. I think there is a potential possibility, but we have not explored it yet. But it
Okay,
is
I see.
possible. It might be possible to to study the Ramon backgrounds in these toy models and then generalize, learn some valuable lessons from it, and then generalize.
So, are there some calculations that are much easier to do? For example, some scattering calculations in 2 dimensions as compared to 10 dimensions, and therefore you can have these checks more precisely.
Um, well, yes and no. So in these matrix quantum mechanics settings with C hat equals one or C equals one, there is a dual matrix quantum mechanics, and doing the scattering calculations in the gauge theory is very easy. It's basically a system described by free fermions, and Moore, Plesser, and Ramgoolam wrote down the exact S matrix. But if you try to actually do the string theory calculations, they are very hard because they involve calculating uh, correlation functions of this Liouville theory, which in principle are known but need to be numerically calculated by stitching together the DOZZ structure constants and the uh, correct conformal block.
See,
So the string theory calculations are done numerically. Now, in some cases, we have been able to use some tricks because there are some simple operators in these theories such that they are total derivatives. So then, you can use some tricks of reducing the moduli space integral to some boundary terms, and then you can get some analytic results.
I see. So, correct me if I'm
Sorry,
wrong,
just to
but
also emphasize
yeah,
the
sure.
value of toy models. So, even in the C equals one setting of computation of d-instanton effects, there was a mismatch that had been noticed by Ashok Sen in the matrix calculation and the string calculation. And in also a collaboration with him, we then simplified the problem even more. We said, let's not even study C equals one. Let's study the C less than one models, which are even simpler. And they have this special operator, which can be written as a total derivative. And by analyzing the problem analytically in that setting, so no numerics, no anything, we were able to identify the source of the problem. And that bug was there in the other calculation as well. So you see that, the details are important in all of these things. And so having toy models that are simple and exactly solvable and analytically tractable is very, very valuable.
I see. As you said before, that there are also these, Ramond fields in the type 0 and type 0b in 2 dimensions.
Yeah.
So, as we were talking before, that for example, in the 10-dimensional setting, we have this pure spinor formalism that tries to deal with the Ramond
Yeah.
fields. So, do you know if there are any, any other formalism that becomes possible in 2 dimensions, which, allows you to deal with the Ramond fields in the 2 dimensions?
No, not that I know of. Because I think,
Okay.
okay, yeah. Is because even the standard formulation is in the RNS formalism.
Hmm.
So,
But it doesn't become easier in 2 dimensions. That's what you're saying.
well, I have not studied the pure spinor formalism. It might be that the pure spinor formalism becomes easy in
Okay.
in 2D. But the point is that these are not free fields. In 2D, you have this Liouville theory, which is part of the worldsheet CFT. So
Mm-hmm.
now, since I haven't studied pure spinor, I don't know how to write the Liouville CFT in terms of pure spinor variables. Maybe it's possible.
I see.
I'm not.
I
I'm
see.
not sure.
So, correct me if I'm wrong, but I do understand that the Liouville theory has this continuous open string spectrum, right?
Even closed
So,
string spectrum is continuous. Yeah.
yeah, even closed string spectrum is continuous. So, does that make things hard to calculate, or that is not a problem? Because sometimes it makes things hard. The open string, the continuous spectrum.
Oh, well, in Liouville theory, it actually people need to do some integrals numerically, but
Mm-hmm.
that's about it. I think people that's what these papers by Balthazar Rodriguez and Yin do. They just literally calculate there's some these OPE diagrams in CFT that involve the exchange of a closed string primary with some
I see.
continuous dimension, and you just integrate over that dimension with some measure, and you get all the answers. So as
I
far
see.
as I know, it's not a problem per se. People calculate with it, find sensible answers, and
I see. I was asking that question because in
but just to say,
a
sorry,
paper.
not just Liouville,
Sure.
but even a free scalar, like if you have strings moving in 10 dimensions, that
Hmm.
scalar field has non-compact, has a continuous spectrum because the vertex
I
operator
see.
e to the ikx has dimension k square by 4 and k is continuous.
Right, that's true. Okay, so I was actually asking that question because when I was working on boundary conformal field theory, there we have this condition called the Cardy condition, and Cardy condition
Hmm.
actually kind of tells you that how do you fix the normalization constant of the boundary state, and the
Yeah,
Cardy condition actually hinges on the fact that when you have this open string, this partition function,
yeah,
then it can be written down as a discrete sum of different characters, right? And it says that every coefficient that is appearing in front of the character should be a non-negative integer. But if you have an
yeah.
open if you have a continuous spectrum, then you have an integral, and then this
Yeah.
Cardy condition doesn't make any sense. So I was thinking
No,
that
no.
probably something.
No. This has basically been understood in the boundary states in Liouville theory are very well understood. So there are some boundary
Mhm.
states such that when you put them on these two sides of the cylinder, the open string channel only contains a discrete number of primaries. But then there are other ones that do have a continuous spectrum, but those are all been written down. They satisfy all the bootstrap conditions and so on.
I see.
They're called these
Are you referring
FVZT
to
and CZ boundary states.
right? This is what I was referring to. So you're
Yeah,
referring to FCZT. Okay.
yeah,
Okay,
yeah.
I
The
see.
FVZT with two different parameters on the two sides has a continuous. I should double check, but I'm pretty sure that has a continuous spectrum in the open string channel.
Okay, I see. So now at the end, also want to talk about, if you want to talk about it,
Yeah.
about the string theory community as a whole. So do you think
Hmm.
that the job market for younger scientists is becoming harder and harder, Uh, or do you think that it's not that bad as it is, made out
No,
to be?
I think it is true. It is very hard. Uh, Basically, the pattern I have seen is since I've only been in a few universities that it's people do get a first postdoc somewhere. Sometimes they maybe have to apply for a second year, but it is a little bit punch to the gut, when you have done 7 or 8 years of postdoc and then you are supposed to, leave the field. It does feel sad in some ways, and myself, I've had many doubts whether to continue in the field or not over the years when I was a grad student, when I was a postdoc. Why are we doing this? What is the point? There are all those kinds of confusions. But I do think that, people are not bitter, even when they are leave the field after 7 or 8 years of postdoc. As long as you enjoyed it, you had a good time, you develop really good skills, you end up in a good position. Now, it becomes a bit of a personal question whether you want to spend those 8 years doing a postdoc or not. And I think one should be open-minded in times like this. So one should not, uh, that is would be my advice. For example, now my students in a few years will be applying for jobs, is to keep an open mind and, not to sort of pigeonhole yourself into uh, doing string theory, even when, you're sacrificing a lot of other things in life. You have to find your balance. Like there is no formula in life to have a happy, successful life. And basically, at some point, it comes down to this. Is it worth the sacrifices you are making? Are you getting enough of a kick out of it by doing research in HepTH to make all the sacrifices you're making in terms of, maybe money or family and things like that. So you do have to, take a judgment call at some point, and that's part of it is you have to know yourself. Uh,
I
like
see.
I feel that I kind of got into string theory almost by default, as I was saying, that I was good at math and I kept doing this theoretical physics and I was sort of good at it and I got this job. I mean, it was hard. Like for example, I tried getting a job in the US. I was got one place and one place in India, so not that many options. But um, it's really about knowing yourself, what you want to do. Once you are 30, life starts to look more finite, and um, maybe 35, when you're 35, it starts to look much more finite. And then, you have to make a decision on how do I want to spend the next 35 years of my life or the next 10, 15 years of my life. And it really becomes a call about your value system and what makes you happy. Uh,
Mhm. So do you think that,
but just to answer your question originally,
sure,
yes, I do think the job market is hard, and one should acknowledge that fact. And help
right?
students, when they are not finding postdocs or having a hard time, to help them find other jobs or other fulfilling, careers.
Right. I've seen that a lot of physicists from the HepTH community either go to industry or go to finance, right? So okay, so you have not done that yourself, but you may have seen people doing that, right?
Yeah, yeah,
So do you think
lot of
that
people. Yeah.
right? So do you think that this transition is very hard, or do you think that it's not that hard for physicists?
Well, I have talked to some people. Many people
Mhm.
love it. Like they actually realize, oh, maybe I should have left the field earlier.
Okay.
Many people have that reaction. Why did I continue doing this? I love it here so much. I mean,
Hmm.
I know people like in all sorts of, like, people have gone to Facebook doing just engineering, to machine learning, to finance, to environmentalism, various things. And, people are many of them are happy. Uh, my advisor said this, that everyone he talks to who has left the field seems happy. That's not true for people who are in the field. So,
I can
you know,
understand.
in some sense, one should not feel bad that one had to change paths.
Sure. Well, as you were saying earlier, that if you are in the field, you are, most probably making sacrifices when it comes to money, for example. And of course, when you are leaving the field, then you don't have to make those sacrifices anymore. So there is, a lot of reasons. There are a lot of reasons to be happy. But what I was, referring to was that if you if your skills are in theoretical physics, then is it true that you need to learn a lot of skills before going to industry? Do you think that this is true, or no, that's not
Well,
exactly true?
I think it is true that one has to train. It is
Hmm.
not true that if I'm a theoretical physicist, just tomorrow I can go apply, to a finance company and I will get a job. I think that's just not true. One has to train oneself. But
Hmm.
because, after a postdoc or a PhD, you have that much more maturity in thinking about problems, and you do have a math background, so things come to you more quicker. But there is a training period required. Like even the smartest students I work with, who are like 8, 10 years younger than me, had to, train for a full 6 months, a year to get the best finance job, for example. So it's not trivial. Even all the machine learning people, the people who have gone to machine learning jobs in OpenAI or Anthropic, are very competitive these days. One has to spend at least a year, trying to learn some of those things before one can be competitive in those interviews. It's definitely not automatic.
Hmm. I see. So what you're saying is that it's not that easy, but it's not that hard either, right?
Yeah, let's say give or take a year. It takes you about a year of dedicated learning of that field in order
Hmm.
to be, really competitive at the best places. Uh,
I see.
And a year is a big time in some context. Like if you're a
Hmm.
postdoc, you're doing it in parallel with your postdoctoral research, and you know, so
I
it's
see.
non-trivial.
And one more thing that I want to ask you is that, I'm sure that there is no hard and fast rule for that, but if you can give any ballpark for the listeners. So, if you are in your PhD, is there a number of papers that you need to have in order to have some reasonable chance of getting a postdoc? Or I'm sure that there is no hard and fast rule for that, but any ballpark,
I think three maybe.
at
If
least
you have
three.
three good papers, 3 to 4 good papers in your PhD, I think that's maybe three, not even four. But they need to be sort of, if you have three papers, there need to be three sort of good papers that people sort of, and it's hard to write three good papers in, 5 years, especially if you're applying in your fifth year and your first year, you're maybe only taking courses. So you really only have year number 2, 3, and 4, right?
Right.
Writing three papers in 3 years is not easy for a student. So, so
And
even
yeah, and I also want to ask you that. So this is something. This is the question that I have struggled a lot with in my PhD. So do you think that a student should work on diverse areas in their PhD, or do you think that a narrow tunnel is better?
Um, working, I'm not sure. Maybe working on a narrow thing is okay, but one should be definitely be learning other topics and going to seminars on other topics.
Yeah, that's fine. But
So,
what about working on diverse areas?
but that is, I think, not, sometimes it's not possible. Sometimes
Okay.
you are in a place where there's only two people in the string theory department or the high energy physics department, and you're working with them. So I mean, there are very few big departments now, so it's hard to diversify in that sense. And I think people who do that are in some sense lucky, but I don't think there is any disadvantage in being, focused in the papers that you write during your PhD.
I understand what you're saying. So you're saying that there is no disadvantage. I completely agree with that. And you are also saying that sometimes it's not possible. I also agree with that.
Yeah.
But if somebody manages to do it, do you think that there is some disadvantage with working in diverse areas?
No, no, there is definitely no disadvantage. That's not what I said.
Okay.
Yeah,
Okay.
yeah.
Yeah. Yeah.
So there's no disadvantage in working in diverse areas, but I'm saying it's not completely necessary. It's not necessary for you
I
to
agree.
be a good, high energy physicist. But
And I
definitely one should, have a broad education and culture, within the field. That is very important.
Sure. And when I say diverse areas, I also mean that if somebody wants to work on, for example, some foundational question and not string theory itself. So do you think that that will help or no?
Oh, sorry, help means what?
Well, help you in finding a job, right?
But foundational in what sense?
So,
What
for
what
example, foundations of quantum mechanics.
Well, that's a hard field. I
Yeah,
myself, think that there are things to be done there and people should think about it, but you might have a harder time finding a job with foundations of quantum mechanics than string theory, right?
right.
So,
Well, what I'm saying is, I suppose that there is someone who has 3 papers on string theory and one
mhm.
paper on foundations of quantum mechanics. So, do you think that that one paper will even count for the jobs or not?
I would say that having been on the other side of the
Mm-hmm.
hiring cycle, unless that paper is sort of very solid on foundations of quantum mechanics and that it has gotten some attention,
Okay.
it might just be ignored. I mean, if there's a panel of, high energy physicists reading it, and
Mm.
that paper is just there as, oh, I wrote this paper, and there is no strong, punchy conclusion there, like most likely people will not. I mean, because, the readers themselves don't have that knowledge to judge that paper. So,
Right, right.
it ends up depending on which group you applied to for a postdoc, right?
I agree. Okay.
Yeah.
I see. So, okay. So when I announced this podcast, I asked some of my,
Mhm.
audience for their questions, and some people
Yeah.
sent me some questions to ask you. So I'm now,
Mhm.
now going to ask you some questions from the people.
Yeah.
And most of them are students, of course. So the first question is that students have this tendency to think everything intuitively or hand wavy and neglect the mathematical rigor. How does one avoid this trap?
Well, I wouldn't generalize it. I would say maybe some students have this tendency, not many.
Yeah, I
But it
agree.
is true that one should do calculations. That is the one thing that you absolutely have to do. Like a good way to think about it is to what my colleague at Stanford, Douglas, told me once. It is to think of it as creating problem sets for yourself. It sometimes helps me now to sort of write, these are the 10 things in worldsheet string theory that I need to calculate. These are the 10 things that have appeared many times, but no textbook is deriving these 10 formulas. So I need to sit down and derive these things. So the art is really to know what calculations to do yourself that you really must know, you know. So one has to think of it really that way, because unless you do calculations, simple calculations, and convince yourself of basic facts over and over again, uh, it is very hard to be successful. And that is
Hmm.
my biggest advice, is to, be humble in terms of what you speak, and how what you're saying connects to the calculations that you have done, because people also have this tendency to just, blather on with some jargon and without really deeply understanding what they're talking about, especially in competitive departments. And that is something that you should definitely avoid. Like, keep your
Right.
hands dirty with calculations, write notes. Yeah, just keep in touch with calculations. That's the only way to succeed.
Right. And when you mentioned Douglas, you mean Douglas Stanford, right?
Yeah.
I see. Okay, so the next question is that I would love to hear his perspective on how upcoming AI developments might reshape the work of theoretical physicists over the next 5 to 10 years. Specifically, I'm curious about which skills he thinks may become more or less relevant as AI continues advancing.
To be honest, I haven't thought about this question.
Hmm.
I I can give you some answer that mathematicians like Terence Tao have been advocating now to this for math. I mean, there the answer is a little bit cleaner, because basically what they say is you use the AI to generate guesses or generate a potential proof for some problem. And then they have these formal theorem checkers that they can run on the generated proof and kind of tweak it, in order to get a true honest proof. Now, in physics, you don't have that second part. You don't have an automatic theorem checker, because we are not proving theorems. Our results are not rigorous. So this sort of paradigm of AI guessing something, and maybe it is still useful. Maybe the AI can supply you with some guesses, and then you can sit down and check those guesses, which is very important, because that the AI doesn't guarantee correctness. So in terms of generating ideas, generating educated guesses, it might be very important. But right now, I do think that this chat GPT training is quite bad in string theory. Like even if you ask some basic questions about what is the scaling dimension of the beta gamma ghost, or what is the BRST current in worldsheet string theory, it just gives you the wrong answers. I have done it many times, and so one has to use it with caution. So it has not been very useful at the level of ideas for me yet. I do use
Right.
it for sort of mundane tasks like drawing a Tix figure or something like that. It can do. Now I start putting Tix figures in my notes or something.
That's a good idea. Actually, I should try that. To use text figures from ChatGPT. That's
Yeah,
interesting.
you draw it on a piece of paper, you tell it, write the
Sure.
Tix code for this.
Oh, that's great. Okay, so I actually have a follow-up question or a follow-up comment on that. So you mentioned that you were interested in string field theory, and we also had Harold Urban on the podcast. So he works on
Hmm.
string field theory as well, and he is using AI to generate the guesses for closed string vertices. So do you think that that's one area where, for example, you can use AI?
Yeah, definitely. I think Harold and Atakan Firat had a paper that I heard a talk about. So
Hmm.
definitely, any computers have to be required, even in string field theory. If, like think of lattice QCD. Wilson wrote down the action, but to do any calculation with lattice QCD, you need computers. So that's a fundamental theory for which you need computers. Similarly, if one day, you find the ultimate formulation of string theory, whatever it might be, you probably will have to use computers, to do it. But more practically today, they are still useful, right? Like Harold is using them, and
Right.
AI or whatever tools. I'm not against using AI as a tool at all. Like I think one
Sure.
should harness its power and do just use it to whatever one wants to do. So far, in my own research, it has not been useful. Let me just say that.
Right. Okay, so the next question is actually a bit related to the question that I just asked you, and probably you have answered it already. But if you want to say something else to this question, you can. So the question is that does the future in string theory have to be too much computer dependent, or still hardcore theoretical research can still function in the 20th century? Sorry, in the 21st, sorry, in the 20th century non-computer way.
I think this non-computer way is not really a thing anymore. So.
Mm-hmm.
uh, I mean, one has to be, I think, if you're attached to a certain problem, you should be willing to use all the tools possible to solve it. Um, because once things get more complex, there is just no way to avoid computational tasks, right? Like, so one just has to do it. Even the initial string field theory computations in the open string field theory, finding the tachyon vacuum. People were just doing sort of numerically solving this Witten's cubic string field theory before the analytic solution was found. Like people like Ashok Sen and Martin Schnabel, that's what they were doing. They were just doing numerics on this Witten cubic open string field theory, and finding the coefficients in that tachyon vacuum state to very very high orders. And
I see.
so computers are just have to be used. I think there is just no way out.
I see. Okay, so the next question is that can you please ask him the path to theoretical physics for someone in India, like what things he or she must do to have a path in
I think
theoretical physics?
theoretical physics paths in India are actually very well established. We are
Hmm.
lucky to have a big community, and in December, for example, every year we have this Indian Strings meeting or National Strings meeting, to which 100 people come. So it's a big community, and basically you do an undergrad at some university or college. It doesn't have to be even in science; it can be a engineering undergrad. I'm working with one student in ICTS right now who has an engineering undergrad degree. And then there are these exams that you can take
Hmm.
to come to TIFR or ICTS or CMI or various other institutes for your PhD. And so there are just regular set paths that you need to take. Just do a bachelor's from some college that has good science. Even if you're doing engineering, you probably need to have some good physics courses if you want to do physics in your PhD. So make sure you choose your college accordingly. For example, there are these IISERs, which are Indian Institutes of Science, Education and Research, which are different than the IITs. And they have been producing some amazing undergrads in the last like 10 years. Like either Bhopal, either Pune, either Kolkata, like they train their undergrads really, really well. And many of them, go abroad for their PhDs. And it's just very, very impressive. So one
Right.
doesn't need to do anything out of the ordinary. There are just normal colleges you can go to and get very good training.
I see. Okay, so again, we have kind of addressed this question before, but if you want to say something else to this question, you can. So the question is that with all the criticisms that string theory is facing, which seems to be getting harsher and harsher every day, how does one motivate himself or herself to pursue this field for a PhD?
Again, I think, yeah, as you said, one thing that one needs to realize is that these criticisms of string theory are by people who are not that well informed, in my opinion.
Hmm.
They undermine these huge successes of string theory that we have talked about, and they don't talk about the fact that we don't even yet understand what the theory is a theory of. It's definitely not just a theory of strings. So it is still in its infancy. The kind of possibilities that exist and the number of questions that need to be answered are very large. So one, doesn't hopefully doesn't need more than that to be, driven to solve these. Now, I should say that though a little bit of the prerogative falls on the older generation to counter some of these criticisms on a public forum. I can say these things, but I do feel that some of the more prominent people should realize that the younger generations are getting affected by this negative propaganda against string theory. And so somebody from some like, senior string theorists do need to sort of be a little bit more uh, in the media attention and, counter those criticisms in a more public way, so that some of these anxieties that the younger generation is facing can be alleviated. Because, people do consume a lot of media these days, even when you're in high school and so on. So if you constantly hear just one side of the story, and the actual string theorists are just quietly, working in their offices, they do need to, make their message heard to the younger generations. And the second point is that I think our field is also bad in producing pedagogical materials for learning that are easily accessible to the younger generations. I have myself struggled with it quite a bit in
Hmm.
learning subjects, for example, that did not have much progress in the last 20 years. So you have to read a paper from 30 years ago or 25 years ago, and it's
Right.
very hard. And I think mathematicians are a very good example. Like, they write books, they care about writing textbooks for even advanced topics. And, once
Hmm.
there is a book, you can read from it and learn from it. Whereas I think theoretical physicists need to do more of that. And in an environment where progress slows down, everyone needs to become more inwardly focused. And, the gaps between big successes are larger. This process of transmission of knowledge from one generation to the next becomes all that more important. So we need to realize that having these repositories of knowledge that someone can learn in an easy and a fun way is very important for motivating new generations to take up this subject.
Right. There are a couple of things that one can say here. For example, this is one of the reasons why I really liked Polchinski, because he used to actually write the criticism, the counters to the criticisms of
Yeah.
string theory. And when it comes to the pedagogical part, you're kind of saying that either books should be written on the subjects that have no significant progress, or for at least reviews should be written, big reviews, right?
Yeah.
And this is one of the reasons why I like David Tong, for example. He does try to write a lot of things for the younger students as well.
Yeah.
Um,
Yeah.
okay, so there is one question. It's a bit sensational, but if you want to say something to this question, you can. So the question is that is string theory the end of theoretical physics as we know it?
But I mean, yeah, what does this question even mean?
I don't know.
I mean, it's definitely not the end of theoretical physics, because let's even assume that there is no one else that takes up string theory after the current, let's say the people who are currently doing string theory, after they're all dead, like no one else is doing string theory. Like theoretical physics is still there, right? I mean, people are doing astrophysics, people are doing cosmology, people are doing condensed matter physics.
Right.
And that is all theoretical physics. So it will definitely not end. I mean, theoretical physics will not end.
Sure. Okay, so the last question, I think you have kind of answered this question when you said that some of your students will be applying. So the last question was that when is he taking PhD students? So I guess you're already taking PhD students. Is that correct?
Yeah, I have one PhD student right now, and yeah, that's one. Yeah, but
Okay.
I won't be taking too many students at a given time. So
Okay, I see. Okay, so the last question is that do you have any advice for younger scientists, before we
yeah,
go?
my only advice is that uh, if you have already made a decision to do theoretical physics, keep your hands dirty with calculations.
Mhm.
Uh, don't fall in the trap of just talking jargon without understanding it. That is the biggest thing. And learn diverse topics like we discussed, like learn quantum information theory, solid state physics, QFT, like many of these things sort of cross fertilize each other. That's very important. And ask questions, like, as this is something I found with students in India and maybe students from the Eastern cultures generally, that they're kind of hesitant to ask questions during seminars. They think that it will come across as silly, or they will, you
Or
know,
disrespectful?
or feel like that they're slowing down the talk or something. I think that should definitely not be the case,
Hmm.
because you have to just ask the question. If you're following for 10 minutes, you ask a question, you'll follow for the next 5 minutes. And then the next talk, you ask a question at the 15-minute mark, maybe you'll understand 2 more minutes of the talk. Like
Right.
it's very important to understand that any kind of research is as much a dialogue as it is, doing calculations or experiments in solitude, because that is how you generate ideas.
Hmm.
And you will only be able to talk in confidence when, your things are clear, when, you have some clarity in your mind about what the talk was actually about. So
Right.
have those conversations, ask those questions, and, talk. You learn a lot by talking to your colleagues, to your peers. So continue to do that.
Sure. So based on some of the talks that I have given, and surely you have given much more talks than me, and I think you can watch for the thing that I'm going to say. The speaker actually likes it when you ask question. I mean, the speaker
Yeah,
doesn't
exactly.
dislike it,
Right.
right?
Yeah. Yeah.
Right.
Yeah. And the other thing is, like, even before, so for people who are still deciding whether to do a PhD or not, my advice is, like, think hard about what you're getting into and why you are doing this, because
Mhm.
it's 5 to 6 years of your life. And the answer shouldn't just be, oh, this is the thing that people do after undergrad. Like, you should have at least some kind of um, direction, at the end of 4 or 5 years of undergraduate degree, that this is something I like, this is what I want to explore more. And definitely, if you're entering theoretical physics, I mean, more specifically, formal high energy theoretical physics, be prepared that there might not be jobs at the end of the PhD. And, so you take a decision to do it, knowing that even if you do very well, you might not get a postdoc. So one has to be kind of okay with these kind of things. And
Mhm.
then it can be really fun, then you just go and you know that I'm here to learn these things. I'm here to just um, become a mature thinker, become a mature problem solver. And that's what I want to do, in the PhD.
And you may have to transition to industry or finance after that. I mean,
Yeah,
that's
that
very
that is, that, I mean, that is inevitable. I think if we don't tell that to students, we are just like lying, like, so that one shouldn't do.
well, inevitable in a lot of cases, but not always
In a lot of
inevitable.
cases, not all the cases, that's what I'm saying. So one has to be, I mean, there's a certain statistics, right? Like, if you're entering, you don't know how it's going to go. So
Sure,
one
sure.
should not expect that you will land like a good solid postdoc, one or two, or a faculty job at the end of it.
Right.
I those guarantees are all off.
Okay. So I think my questions are over. Thank you so much for your time. It was a
Okay.
great pleasure to talk to you. So,
Thanks, Hassan. It was
thank you
fun.
for your time. So if you like this video, give it a thumbs up and consider subscribing. And the YouTube algorithm thinks that you will also like this video.